Okay, today's business, we'll be talking about structure of materials, because we have studied different models that helps in understanding solids. We have checked spoken about different models, their successes, their shortcomings, but we've not even spoken about the structure of materials. We've been talking as if sodium and aluminum, they are of the same structure, or sodium and zinc. We've been talking as if every material in nature have the same arrangements, have the same electronic properties and the likes. So, but from now we'll be trying to distinguish materials by their structures, and one of which we'll be talking about is the periodic table. The periodic table is something you must have learned in, let me say, GS2 or GSS3. And that's another reason why you should be careful with your notes, so that your younger ones will not say you are in 300 level, but they are teaching you the same thing. So we'll be talking about periodic table, just like we spoke about in secondary school, because we may just go a little bit into more detailed, into more than what we did in secondary school. So periodic table is majorly like the work of chemists, but you cannot really separate a field in science to say this is completely chemistry. They also have some aspects in biology and physics as well. So we'll be trying to look at the periodic table from a physicist's point of view. And the periodic table is still the normal periodic table. You know, I think I have the image somewhere here. This is the periodic table I'm referring to. There is nothing special about the periodic. There is nothing new about the periodic table, rather. So we'll be talking about the periodic table from the physicist point of view, and that leads us to talking about. We'll be talking about the 4 quantum numbers. N is a principal quantum number. L is the azimuthal quantum number. L subscript Z is the magnetic quantum number, while the sigma subscript Z is a spin quantum number. So these 4 quantum numbers for every particular element should be distinct. So they help in describing, even for every electron, for every electron on a particular element, their quantum numbers must be unique. They should know 2 electrons should have the same set of quantum numbers. So as we go on, we'll be seeing the differences between these 4 quantum numbers. When we talk about, let's talk about the 2 popular elements. Let's say, for instance, let's talk about sodium. I'm sure you are very used to sodium. When we talk about sodium in chemistry, SS1 chemistry, they tell, even GS3 integrated science, they tell us sodium has 11 protons, 11 electrons, and is it 12 neutrons or so. So, but what concerns us is the charged particles amongst them. And and they tell us that the electrons, they move around in orbits. They tell us that in the first 2, the inner orbit, it carries 2 electrons, while the outer orbit carries 8 electrons. And when we count all the electrons we have now, they are 10. And they tell us there should be another orbit outside there. We should carry the last electron. So the principal quantum number of the electrons here can be said to be 1. The principal quantum numbers of the electrons here can be said to be 2. The principal quantum numbers of the electrons here can be said to be 3. So under a particular principal quantum number, there are sets of azimuthal quantum numbers you can have. So, and under the azimuthal, there are set of magnetic quantum numbers you can have, and under the magnetic, there are set of spin quantum numbers you can have. And in chemistry, they also taught us that for sodium, if we want to talk about the arrangement of electrons on the orbit, we say 2, 8, 1. And later they would come back to say it is not 2, 8, 1 again, it is, they say 1s2. They say 2s2, 2p6, and they say 3s1. So when you add the indices here, 2 plus 2 plus 6 plus 1, it gives us 11, which is equal to the number of electrons in the sodium atom, which is also the same thing as 2 plus 8 plus 1. So the first 2 electrons here is being accounted for right here. These are the first 2 electrons. They are having principal quantum number 1, and they are in the s orbital. They are in the s orbital. So, and when we are saying the s orbital, we are referring to, when we are saying s orbital, when we are saying s orbital, we are referring to L equal to 0, the azimuthal quantum number being 0, and that is, and when we are referring to P, we are talking about the azimuthal quantum number to be 1, and we're saying D, the azimuthal quantum number is 2. So just like the principal quantum number ranges from 0, so the principal quantum number starts from 1, 1, 2, 3, just like we have called this 1, 2, 3. The azimuthal starts from 0. So for every principal quantum number 1, we can have a single S. We can have a single suborbital, which we can call S, which the L, which is corresponds to L equal to 0. And when we move to the next shell, the next next orbital rather, when we move to the next orbital, it is having 8 electrons, and that is n equal to 2. When we are talking about n equal to 2, we are talking about this 2s2 and 2p6. When you count the indices of 2s2 and 2p6, you will notice that they add up to 8, which is equivalent to the number of orbital that we have called principal quantum number 2. There are 2 shells. We have the S shell, the P shells. So under this S, which is having a maximum of 2 electrons, we also have 2p6. There are also P shells, which are housing 6 electrons. Then after that, we move to the 3rd orbital, which is the principal quantum number, which has principal quantum number 3. And because it's a single electron, it starts from the S shell and occupies the S shell. That's how we have it as complete as it is. So like I've said earlier, each of these electrons, they have their unique addresses. Like we're having 2 electrons on this orbital, on this shell, like we're having 2 electrons here. It means one electron is spinning up while the other is spinning down. So the 2 are also unique. They are not identical in any way. And the same thing applies to 2s2. When we come to 2p6, under 2p6, because it is P, and we are talking about P being L equal to 1, we can also divide them into different subshells that will help us in distinguishing their properties. So before I move further, let's take a look at what we have here. We spoke about in these lines we have here, n is the principal quantum number. It starts from 1. They are integers 2, 3, 4, and so on and so forth. While L is the azimuthal quantum number, which starts from 0 and proceeds to n minus 1. So when n is 1, the maximum L you can ever have will be 0. So when you look at this, our n is 1. The maximum we can have is 1s. We cannot have 1p because s is 0. And the maximum we can ever have under the azimuthal quantum number is 0. So, but when n is 2, the maximum we can ever have, because L should terminate at n minus 1, when n is 2, we can have L equal to 0 and L equal to 1. That is, we can have S and we can have P. So the 0, 1, 2, 3 we have here is as good as saying SPDF shells. So the SPDF shells corresponds to the 0, 1, 2, 3. So when the number of the principal quantum number, when it is also 3, the maximum orbitals you can have will be 2. That means you'd have 0, 1, and 2. So when S is equal to, in this case, for this particular orbital, N is equal to 2. That is why we have 0 and 1, 0, 1, and 1, S and P, S and P. So we cannot have anything called 2D shell. We can only have 2S and 2P, nothing like 2D. But when we move to the third quantum number, we can have as large as azimuthal quantum number 0, 1, and 2. And that corresponds to S, P, and D. When we have S, P, and D, it means that when we have S, P, and D, it means that if the number of electrons for the right now we are considering sodium. If we are talking about some other elements with large number of electrons, we may need to talk about 3p, 3d. So, but for this scenario of sodium, this is where we stop because we've counted 11 electrons. So for each of these azimuthal, they also have corresponding magnetic quantum numbers. For instance, when L is equal to 0, the magnetic quantum number ranges from minus L, increases up to plus L. So from minus L to plus L. So when L is 0, it ranges from minus 0 to plus 0. That is, you would have just a single value of a magnetic quantum number. So when you are dealing with L equal to 0, when you are dealing with S, you can only have a single magnetic quantum number, which is L subscript Z equal to 0. When we move further to P, which is L equal to 1, then under L equal to 1, we'll be talking about from minus 1 to 0 to plus 1. That is, for P, we'll be talking about the magnetic quantum numbers Oh, sorry, I shouldn't write in that corner. We are talking about P. Then we should be talking about magnetic quantum numbers -1, 0, and 1. So when you look at this particular shell, 2p6, it is carrying 6 electrons. And for the fact that it is carrying 6 electrons, some of the electrons are having, 2 of the electrons are having -1 as their magnetic quantum number. 2 of the electrons is having 0 as the magnetic quantum numbers, while 2 of the electrons is having 1 as the magnetic quantum number. That means 2 plus 2 plus 2 equal to 1. So when we now look at it again, 2 is having -1 as the magnetic quantum number. 2 are having 0 as magnetic quantum number. Another 2 are having 1. So the 2 that is having -1, for instance, when you look at their history, those 2, they have the same principal quantum number 2. Those 2, they have the same azimuthal quantum number, which is 1. Those 2, they have the same magnetic quantum number, which is -1. But those 2, one will be having a spin of -half, while the other will be having a spin of +half. And that is why each of the electron in an atom will be unique when we describe them in terms of their quantum numbers. Do you have any questions before we move on? Okay, so let's, I have a table here. Okay, I'm listening. Okay, okay, said no. Okay. I believe silence means consent. If you don't say anything, I believe it is no. So let's reserve the slot for those that need help. So I designed this table from what I've been talking about for the past few minutes, which is talking about a particular shell. The particular shell is having principal quantum number 4. So for the fact that it's having principal quantum number 4, it will have S shell, it will have P shell, it will have D shell, and it will have F shell. And if you read the paragraph above this table, over there, I wrote there the maximum number of electrons that an orbital can accommodate. For S, it is 2. For P, it is 6. For D, it is 10. Hello, are you sure you're not the only one not hearing me?
I can hear you, sir.
Please check your end. It must be from your end, because I'm not having any sign of having network challenges here. So please fix from your end. So, and F is 14. And the formula for arriving at these numbers, when you make your S to be, when you remember that your S means L equal to 0. Let me take another color. Well, you know that your L means L equal to 0, L equal to 1, L equal to 2, L equal to 3. So for every, for the fact that we have a principal quantum number n equal to 4, the L, the azimuthal quantum number we can have, would start from 0, 1, 2, and 3. And for every 0, we have the magnetic quantum number will be 0. For every 1, it will be from -1 to +1. For every 2, it will be from -2 to +2. For every 3, it will be from -3. So there is I would have to correct this. I'm just saying this right now. This should be from -3 to +3. It's a mistake. This should be -3. This should be -3, -2, -1, then sorry, -1, then we should have 0, then we have +1, +2, and +3. I'll correct this and update. So the L should range from this should range from -3 to +3, and each of the magnetic shells, magnetic quantum numbers, they would have 2 different spins, 2 unique spins, which is -half and +half. And when you count, so at the end, 1 electron would have on that particular orbital that we are, that particular orbital with quantum number 4 that we are considering, all of them, let's assume the orbital is full and it's carrying 2 + 6 + 10 + 14. That is 20 + 12, 32. All of them, all of the electrons are having principal quantum number 4. Some are having 0. Some are having azimuthal 0, azimuthal 1, azimuthal 2, azimuthal 3. Part of the azimuthal 2, 1 is having, okay, sorry, out of the azimuthal 0, we can only have magnetic 0. We can only, when azimuthal 1, we can have -1 to +1. And when we look at this, let's just deal with this and leave this table. This -1, all the electrons, the 2 electrons having this -1, have the same address until we get to the spin. And one will be spinning up while the other will be spinning down. For that reason, on that particular shell, we'll be having unique sets of quantum numbers. So I think I've done enough justice to that. So, and like I said in the video on the concluding parts of yesterday or last lesson, the video I put online, that in nature, the lower energy levels are usually favored in terms of occupancy, the lower energy levels. So when we are saying that, when we are saying principal quantum numbers, if we want to talk about the energies of those orbitals, the n equal to 1 has a lower energy compared to n equal to 2. So as n increases, the energy of the level of also increases. So when we are talking about the filling of electrons, it should start from energy levels that are smaller. It should start from energy like 1 before we move to 2, before we move to 3. But also, when we are talking about, there are also some other things to also put into consideration, which is for the fact that we have something like, let me bring out the pen. The fact that we have something like 3 sp 3d, or let me say 4f, and we also have something like 3s. Somehow there is a way we look at it and we say that this 3s, okay, sorry, I'll talk about something like when we talk about something like 4s, I'll talk about something like 3d. there is a way we look at it and we say, no, for the sake of this D, it has made this 3 to be stronger than this S, this 4S. So, and that takes us to Aufbau's and Madelung's principle. Aufbau's principle is very straightforward, and it tells us that shells must be filled from the lowest available energy state. And when the lowest available energy state is completely full, then we'll move to the next higher available energy state. So we don't start filling the higher energy states if the lower energy states have not been completely filled. So, but not all the elements obey that rule anyway, but that is Aufbau's principle. Madelung's rule tells us about the ordering, and the image we have here is talking about Madelung's rule. So, yes, come on. So, and I should have even come here earlier. I think this is very straightforward to look at. So look at this figure. When the principal quantum number is 1, the maximum L you can have is L equal to 0, which is S. When it is 2, L equal to 1, which is P. When the principal quantum number is 3, the maximum L you can have is 2, which is equivalent 0, 1, 2, which is D. So, and so forth. The shells are painted red. Those ones, they are, for now, they are not existing. You can't find any element on the periodic table having these values. That is why they are in color red. And what else should we talk about? And these arrows, the way they are pointing is showing how the shells should be filled. So when we want to fill the shells, we should start from 1s1. When we're talking about sodium earlier, we spoke about sodium to be having 11 electrons, 1s2, 2s2, 2p6, and 3s1, adding up to 11. And the reason why it was convenient to write that way is because the first arrow we deal with here is, the first orbital we'll deal with here, according to this arrow, is 1s. After 1s, the next one is 2s. After 2s, the next thing is, we come here, the next thing is 2p. After 2p, the next thing is 3s. After 3s, next thing is 3p. After 3p, the next one is 4s. After 4s, then we come to 3d, then 4p, 5s, then 3d, 5p, 4s. And this diagram is a consequence of Madelung's rule, which says that the ordering should start from the lowest n plus L. The lowest n plus L. When we attempt to write this in terms of n plus L, we'll be talking in terms of saying S is 0, then we can say 1 plus L. 1 plus 0 is 1. 2 plus 0, 2. 3 plus 0, 3. 4 plus 0, 4. 5 plus 0, 5. When we come to the next column, P is 1. 2 plus 1, 3. 3 plus P here, 3 plus 1, 4. 4 plus 1, 5. 5 plus 1, 6. When we come to D, 3D, D is 2. 3 plus 2, 5. 5 plus 4 plus 1. Oh, sorry, I said 3 plus. What am I saying? D is equal to 2. 2 plus 3 is 5, or rather 3 plus 2 is 5. 4 plus 2 is 6. 5 plus 2. 5 plus 2 here is 7. Then let's come to this corner. F is 3. F is 3. 4 plus 3, 7. Let's come here. F is 3. 5 plus 3 is 8. Let's come to this corner. G is 4. And 5 plus 4 is 9. So when we follow Madelung's rule, it tells us that after 1, the next one is 2. After 2, the next one is 3. But now we have 2 3s on this figure. We have 2 3s. For the fact that there is a conflict, 2 3s, it asks us to stick with the one. We should settle the quarrel with the one with the lower n. This is having the lower n. This is n equal to 2. This is n equal to 3. But their n plus l are equal. So to settle the quarrel, we'll take this. This should have precedence. And for that reason, this. Oh, sorry. This aligns with this. The next one here goes with this. Then now we have 2 4s. This 4 will take precedence. Then this 4 next to this 4. Then next is 5. So we talk about this. You can see that we are just talking about this particular 5. We are just talking about this particular 3D, even after talking about 4s. And that is Madelung's rule of in terms of occupying orbitals.
Hello, sir.
I'm getting.
Please, sir, can you, the Madelung's rule, can you come again, sir?
You should have read it, but I posted it very late anyway. Madelung's rule states that when we are filling the orbitals, we'll fill from the lowest n plus l. We'll fill from the lowest n plus l to the highest n plus l. And when we have 2 n plus l for a particular shell having the same, or when we have 2 n plus l's, 2 shells having the same n plus l's, we should settle the quarrel by which of the n plus l have the lower n. So the n plus l that has the lower n will take precedence. And that is exactly what this table shows, or this figure shows. So is it clear?
Okay, sir.
Okay. So from Madelung's rule, I've put up here. Ion, for instance, ion is Fe. It's having 26 electrons. We start with 1s, 2s, 2p, 3s, 3p. We spoke about 4s even before finishing 3. So 4s shell has a lower energy compared to 3D shell. So, and we'll be using these words frequently: ionization energy and electron affinity. So it's good to be familiar with the definition. Though I've put it up here, ionization energy is the energy required to remove an electron from a neutral atom to create a positive ion, while the electron affinity is the energy gained by adding an electron to a neutral atom. But this is an example of the periodic table I would like you to study and play with. And one of the unique things about this periodic table is that it includes the highest energy shells. It includes the energy shells, the electronic configuration of the highest shells, they are included. So when you look at, we spoke about sodium earlier, you can see it is 3s. I also spoke about iron, which is 4s2 before 3D. So I think that's for now. So let's quickly talk about effective nuclear charge. Effective nuclear charge is we're talking about sodium, for instance. I think, let me see if I put it here in details. Talking about sodium, for instance, when earlier we spoke about sodium to mean 3 orbitals. This is having 2 electrons. This is having 8 electrons. And the final one outside is having a single electron. And we should also talk about what is at the center. At the center here, we have 10 protons. 4, 5, 6, 7, 8, 9, 10. 11, not 10. We have 11 protons at the center. We have 11 protons at the center, packed together like akara. So the 11 akara or protons at the center are positively charged, while the 11 electrons on the orbits are negatively charged. And the plus 11 protons plus the minus 11 electrons gives us 0, an electrically neutral sodium. So now this effective charge paragraph is trying to talk about what is the experience of this outer electron. What is it even feeling? Because currently this outer electron is not enjoying the nucleus. It's not enjoying the protons, because the protons is already being shielded by 2 electrons, already being shielded by another 8 electrons. So what is it even feeling? So then we are concerned about what is happening around here. What is happening around here? What is this single electron? What is it even feeling? And the straight answer is to say that it is feeling 11 protons minus 10 electrons to enjoy just +1 charge. So it's having, what is experiencing, it is what this proton will be saying will be good as there is just 1 proton here, because the 10 electrons here have the effect of the 10 electrons here have nullified the existence of some other 10 protons here, leaving just 1 proton to be effective around here. So just put that one in one corner of your hard disk. And let's move straight away to another section of this lesson, which talks about chemical bonding. Chemical bonding talks about how the atoms stick together. So, and there are different types of chemical bonding, which none of them should be strange to you. And they are ionic bonding. We have covalent bonding. We have van der Waals bonding, metallic bonding, which again, hydrogen bonding. I think there should be 5 or 6 on it. So in ionic bonding, there is complete transfer of electrons from one atom to the other. So the from the definition of ionization energy, the energy required to remove 1 electron from an atom, the energy increases as we move on the periodic table. The energy, the ionic ionization potential increases, or the ionization energy, if that will be convenient, it increases as we move in this direction. It increases as we move like this. And it also increases. As you move like this. So it increases like this. That means it reduces as in this direction. It increases in this direction, and it also increases in this direction, meaning it reduces in this direction. So that's secondary school level. So, but the point I want to drive out here is that in ionization, ionic bonding, it usually involves elements with low ionization potential and those with very large ionization energies, such that there will be complete transfer of electrons from those.
Sorry, sir, I didn't get that.
I said, what point is it? The ionization potential? What exactly? Once again, what I've said is ionization. Ionic bonding involves complete transfer of electron from one atom to the other. I said it usually
Yes,
involves
I got that,
atoms.
sir.
usually involves atoms with low ionization energy and those with very high ionization energy. So for instance, at this corner, we have very low ionization energy. The energy required to remove an electron from elements in this corner is very low compared to the energy required to remove electrons from the outermost shell of these atoms. So one easy example again, when we are talking to describe ionic bonding, is to talk about sodium and chlorine, which gives us the common salts. So sodium loses an electron. When sodium loses an electron, it will be left with 10 protons. Sorry, my VI is 10 coming to my mouth today. 11 protons and 10 electrons, because it has, when it was neutral, it was having 11 protons and 11 electrons when it was neutral. So now it has lost an electron. For that reason, it becomes +1. The charge becomes +1. Chlorine, which has originally 5. Oh, can I undo that? Aha, good. Chlorine, where is eraser? Come here. Chlorine, which has 17 protons and 17 electrons, is said to be also neutral. Then later, the chlorine, which has 17 protons, collects one additional electron from sodium, and that is 18 electrons. So 17 minus 18, that is -1. So then the charge of chlorine becomes -1 when it receives an electron. So when it receives an electron, when this sodium gives an electron, it becomes a positive charge. When chlorine receives an electron, negatively charged. So that is why our pastor used to tell us that it is more blessed to give than to receive. When this sodium gave out the electron, it became positively charged, while the chlorine is negatively charged. And now, what concerns us in ionic bonding is that a positively charged ion and a negative ion, they would interact, they would have a strong force of attraction. This is positive, this is negative. From, if you talk about Coulombic interaction, it will be attractive, and it attracts to give us a very strong sodium chloride bond, which has a high melting temperature. It's an insulator. It is very hard. It can dissolve in water because it is ionic in nature. So that's the basics. Okay, when you read through these footnotes, I think what I've just said now, the footnotes here should be talking about that of effective charge. Okay, no, everything here is about effective charge. So maybe I thought there is no need for. Okay, so let's move on. So you can go through these equations. They are talking about the ionization energy of A. You can, for simplicity, you can take your A to be sodium and your B to be chlorine. And by doing that, you'll be able to understand the energetics of the ionic bonding. So we talk about the ionization energy, we talk about the electron affinity, and we also talk about the coercive energy. And another way to talk about the tendency of formation of an ionic bond. An ionic bond, will it be feasible? When you take sodium and you take calcium, and you are talking about ionic bond, will it work out? The Mulliken electronegativity values helps us to determine if that is feasible. When you have two materials, two elements having their so these electronegativity values, every element has its own electronegativity value. So when two materials, two elements, when their electronegativity values, when they are very close, the tendency of forming an ionic bond is very slim. So a good condition for having ionic bonding is when the values of their electronegativity is wide apart. When it is wide apart, then you can be talking about the feasibility, the possibility, or high tendency of having ionic bonding. And just like ionization energy, electron affinity, the electronegativity also increases as you move towards the right-hand side of your periodic table. It also increases as you move from the bottom to the top of your periodic table. So, covalent bonding. Let me look at this. Is there anything I should talk about before we call it quits? No, I think they are simple enough. There are things you can just look around and play with. Okay, I think it's time. Okay. So let's quickly talk about covalent bonding. This occurs when the electronegativity values is not very far apart, or let me just say intermediate, not really far or not too close. And in this case, electrons are shared by two atoms. In the case of ionic bonding, complete transfer of electrons from sodium to chlorine, but in this case, two atoms, they would not be able to say, I dash you the electron. I cannot, it's like some of you now, two of you, you are using the same phone to connect to this class. It's like a covalent bonding. You cannot take a phone and be bonded to your phone through ionic bonding. Now you are busy sharing one electron being two atoms. So that is an example of covalent bonding in which the atoms cannot completely transfer or completely receive an electron from the other bonding party. But in that case, the atoms now share the electrons. And the materials of this nature are usually semiconducting in nature or insulating in nature. They are usually hard. They also have high melting temperatures. And there are two ways with which we can easily explain the bonding, covalent bonding, and one of which is particle in a box picture. So the particle in a box picture is shown in this figure. This is a box. This is another box, but we are just trying to view it as a box. This is an atom. This is another atom. So we are trying to view an atom like a box. I was viewing atoms like boxes. So in this diagram, let's take these boxes to be hydrogen atoms. When the hydrogen atoms, what do we expect? We expect an hydrogen atom to have an electron, and since it is hydrogen, the electronic configuration we can ever have should be 1s1. Since it is 1s1, that means that it is at 0 Kelvin, at ground state, it will be the electron of the hydrogen atom will be occupying 1s1, the lowest energy level. So now, just for convenience, we have two here. This one is spinning up, this is spinning down. They were to be spinning the same direction when they come together. So this is one hydrogen atom, this is one hydrogen atom, and this bigger box here is two hydrogen atoms, or let's call it hydrogen molecule. I'm sure that is very familiar when you're talking about hydrogen molecule. Hydrogen molecule is, I think I should still remember chemistry a bit, which is H2. Hydrogen molecule is H2. Hydrogen atom is H. And we say when we are talking about hydrogen gas, it's usually written as is this off? It's usually written as gas. So for we to determine the energy of a particular level, or for the energy of a particular atom, this is the formula that we should be familiar with. The energy being equal to this bunch of constants divided by the width, L, the width of the box, just like the size of the box. So when we are dealing with a box that is one-dimensional in nature, so all we are interested in is dimension L. So it's a one-dimensional box. So as L increases, E is expected to decrease, right? Because this is E is inversely proportional to L squared. So as L increases, E decreases. So for that reason, it is easy to say that the energy of this box is H squared by Planck's the normalized Planck's constant square pi square over 2ml square. It's easy to talk in this way. But when the two atoms, when they come together, they form a bigger box of dimension 2L. For that reason, the L in this particular equation is now replaced by 2L. So when you work this out, you should get something like this should be equal to h bar square pi square over 2ml square, then times 4 times another 4 here for the sake of the 2 here, 2 square, we'll be having divided by 4 again there. So when you work this further, this should be something like h square pi square all over 8ml square. So when the two atoms come together, their energy will become h square pi square over 2ml square. But before, this happened to be the energy of this box, while another similar h bar square pi square over 2ml squared happened to be the energy of this box. So if we had wanted to even add them together, when you add this, the energy of the first hydrogen atom with the energy of the second hydrogen atom, you are expected to have, the only difference you should have is to say that this would disappear. Then these two will disappear, which will even make the, am I right? Yes, which will even make the energy bigger when you add the two energies together. Should have something of this nature. But now, when they bond, you have something very small. And like I said in the earlier, that nature favors smaller energies. Nature favors smaller energies. So for the fact that these two hydrogen atoms will bond to form an energy level that is having a smaller energy, then this is a very feasible reaction, or this is a very feasible bond. And you'll notice something here that, okay, so this formula, there is something missing from this formula. It's not completely complete. There is also something we should add here, which is n square. N square. So for n equal to 1, which is what we have been dealing with, n square, 1 square is equal to 1. So for that, we can easily say that our E bonding is equal to what we have here. But when n is equal to 2, our n equal to 2 will give back to this 2 pi we have here. So we'll be having 2 square. We'll be having, for the E anti-bonding, we'll be having 2 and 1 2 square, which will be here, which is also different from what we have here. So what is E bonding? What is E anti-bonding? E bonding is the energy of the bonding orbital. This orbital that is formed as a result of the coming together of these two hydrogen atoms gives birth to this orbital that is called the bonding orbital. Well, the and that is like the ground states. So now we are no longer talking about it as like an hydrogen atom. We are talking about it like an hydrogen molecule. So when we call this the ground states of the hydrogen molecule. And we should also be talking about other excited states, which would lead to, we're talking about something of this nature, which would give us another energy level above the ground state. So this is the ground state, and the upper one here is the excited energy level, the excited state. And the name of the excited state is called anti-bonding orbital, or the orbital of the energy level of the first excited state is called the anti-bonding orbital, while the energy of the ground state is called the bonding orbital. So they are just terminologies. Don't, but with time you'll see the meaning. Why are they calling it anti-bonding? If you read through the text. So I think I've done justice to that. While we are even, I think this is a mistake. The diagram here is not what I want it to be. I'm going to replace it. Sorry about that.
So I can't hear you.
And that's, you can't hear me, but you are too there. I hope you are I pray you are the only one not hearing me. Can you hear me? Others, can you hear me?
Yes, sir, we can hear you, sir.
We can hear you, sir.
So if you can't hear me, that means the witches and wizards are now sitting on your line. So, but me, I can hear myself. So sorry, I will replace this figure 2.4 as well. I think there are two things I would correct on this course way. I'll correct them today. Latest by 3 p.m. So our time is fast spent, but there are still some things we should talk about. Another picture of covalent bonding is the molecular orbital or tight binding theory. So this is another picture where we talk about the Schrodinger equation, talk about the Hamiltonian. It gives us the same thing we get from the particle in a box. The only difference in this particular picture is that it tries to give a quantitative view of a quantitative view of what we are speaking about in the particle in a box picture. So you'll see several things there. I don't think we don't have the time to talk about this today. Hello, I think, sorry, I had the network disconnection just now. Let me see, cloud drive. Come on, come on, come on, come on. Okay, I was talking about Van der Waals bonding. When you see the, we usually say it is used by witches and wizards, because most of you call wall geckos witches and wizards. Wall geckos, they walk on the wall, they walk on the glass, they even walk on the ceiling upside down without falling down. They even jump on the ceiling, upside down. And how is that possible? Because they have applied van der Waals forces that you have failed to apply. So if you want to learn how to work on the ceiling, you may have to be more serious with van der Waals bonding. So to be a better witch, this is the type of bonding you should try to study, van der Waals bonding. And what else do we have under bonding? We have metallic bonding and hydrogen bonding. Our time is fast spent. I would like to stop now because there are some other things that should be on right now. So how should we conclude this class? We are right here at molecular orbital. Should I make another video and put on YouTube? Do you like that idea at all?
It's fine, sir.
Okay, sir.
Okay, I'll try to make it as early as possible. I won't do it like the one that entered on Sunday. Let me set a target for myself. Let me say by Wednesday, 12 p.m. I'll take it like an assignment for myself. Wednesday, 12 p.m. I'll try to put these things on the channel. So that by next week, we'll be able to start lesson 3 and move. So I think we should call it a day at this point. So we'll meet again next Monday at 12 p.m. Okay. Enjoy the rest of your day. Bye-bye.
Thank you, sir.
Or do you have any question before we call it quits?
Hello, sir.
I'm listening.
I have a question, sir.
I'm listening. Go ahead. What's your name?
Johnson, sir. Johnson.
Okay.
Concerning
what's the question?
You wrote a particular formula, 2 pi. I can't remember. Actually, you added n when you were explaining
Yes.
to it. You added n, but on
Yes.
the slide,
Yes. This is the formula you are referring to.
Yes.
I added n somewhere here.
Yes.
I added n.
But it wasn't
Okay.
on the slide. My question is that, is it the right one, or we should go with the one you sent to us?
It is right, because for the bonding orbital, n is equal to 1. And when n is equal to 1, you would have exactly what you have there. And for the second orbital, which is the anti-bonding orbital, n is equal to 2, which is exactly what you have there. So the reason, if you take your n equal to 2 in this particular e-bonding, you would have exactly what you have in anti-bonding.
Yes, sir. I've gotten it, sir.
Okay. Any question? Any question about the video, about anything that we have done so far? So I think we'll just say bye-bye. Enjoy the rest of your day.
Thank you, sir.
Thank you too.